So we're going to start with talking about particle motion. We're kind of basically focusing in section 3.4 on these applications of derivatives. What do we mean by instantaneous rate of change? How is that affecting a function? Things like that. So last time we talked about applications with geometric figures. If we have a circle and I want to know the rate of change of the area compared to the radius, I can take a derivative. Now we're going to focus on particle motion and free fall, or throwing stuff, gravity, things like that. So a particle moves along a line so that its position at any time t greater than, really should have been greater than or equal to 0, but I did not have access to that symbol without going through some steps that I was too lazy to do. And it's given by the function s of t equals t squared minus 4t plus 3, where s is measured in meters and t is measured in seconds. So often when we're talking about position versus velocity versus acceleration, position is represented by an s of t or an x of t. Don't know why they chose that, but that's the common letter to represent position. So this is a function telling you where you are in relation to some point. If it's particle motion, we're saying it in relation to the origin. All our distances are measured from the center of the line. So first we need to define this word displacement. We're going to find the displacement of the particle during the first 2 seconds. We need to know what do we mean by the particle, or what do we mean by displacement of something. You may have heard it in physics or science class somewhere. What do we mean by displacement? Any ideas?
How far you moved from the origin?
Well, close.
Where you started.
How far you moved from where you started to where you finished. I don't have to start at the origin. I could start here, let's see, this is your guys' negative direction, right? If the smartboard is the origin, I'm at like -5.
Alright.
I can move over here to like -9. What's my displacement from where I started to where I finished? 4. Or I can move back the other direction. I could be at -9, and I'm going to go all the way over here to +3. Now what's my displacement? 12. Because I went 9 units to get to the center, 3 more past. So displacement is just change in position from start to finish.
What's the x of t mean?
X of t is another common way to represent position.
So x of t or s of t?
Mm-hmm. Yeah. Once again, I don't know why they chose either of those. S of t I think you see more commonly in calculus or in physics. X of t you see more commonly in calculus. But I've seen both in calculus. Just most of the time I see x of t. So if we're going to find the displacement, we need to know position. We know time. It said first 2 seconds. So what's the first time we're investigating? 2. But that's where it finished. Where did it start? It says within the first 2 seconds. 0. It starts at 0. I could have also said find the displacement from time t equals 3 to time t equals 7. We can find the displacement for any interval, but if it says within the first 2 seconds, they're assuming you know it starts at 0. So these are the time values, but how are we going to find the position values? Plug it in. Anytime we want to find position, plug it in. Or velocity or acceleration, we need a time value to plug in. So I want to know what S of 0 is, and I want to know what S of 2 is. So S of 0 pretty easy because most things will cancel. So we get positive 3. And then we do S of 2. -1.
Yeah.
So now I want to go find the displacement. How can we find displacement? We talked about what it means, but how did we actually find these numbers? If I was at -5 and I went to -9, how did you actually figure out my displacement?
9 minus 5.
Subtract that. Okay, we subtracted our numbers. So if we take our position at 2, the displacement is really S of, we'll call it final, minus S of initial. So the final time they want us to look at and the initial time they want us to look at. So we just subtract.
Is
-4. So that means initially I would start over here at +3, and my displacement, -4, means I walked -4 steps back this way. So I ended up at -1. So we've talked about average velocity a lot, but you're going to keep seeing it over and over again because it's used in a lot of applications. What do we know the formula for average velocity is? Good. F of B minus F of A over B minus A. So it says over the first 4 seconds again. So once again, we know our final is 4, but we have to assume the initial from that statement. What is the initial? 0. So go ahead and find the average velocity. And when we find average velocity, we do use the position function. We are going to start getting that confused because now we have the ability to find the velocity function. How can I find the velocity function?
Derivative.
Take the derivative. We know the derivative of position is velocity. But to find average, then we actually use position still. So to find average velocity, we still use position function. Because when you do that F of B minus F of A, you get a distance, and when you do B minus A, you have over time, so that becomes a velocity. Distance over time is velocity. So find this really quick. I don't have the answers right now, so it is possible though. That's what you got too? Okay. So when we solve this out, not F, we're using we're getting 0. What are my units? meters per second. They described in the initial problem that this distance was measured in meters, time was measured in seconds. 0 meters per second. So remember, graphically, we're describing a secant line here. Our average velocity is a secant line. So what happened, once again, our parabola is facing up. At 0 seconds, we were at 3. And at 4 seconds, we would have also been at 3. So we're describing this secant line. That's our graphical representation of this concept. That average velocity means somewhere on this function, we also have a velocity of 0. It can change in between, but on average, if you combine all the velocities together, you're actually getting a velocity of 0. So how would we find the instantaneous velocity? A lot of this section is just knowing what do these words mean. So instantaneous velocity. We worked with it with geometry, and it means the exact same thing with position and particle motion. So what do we mean by instantaneous velocity? Derivative. Remember, estimating velocity is average rate of change. Instantaneous velocity is derivative. And we've got to get more used to these words. We've only been hearing it for a little bit, but now it's something we should start trying to translate immediately. Instantaneous velocity means take the derivative. And specifically, when time equals 4, that means I want s prime evaluated at 4. After I take the derivative, I want to plug in the value of 4. So if our original function, I'm going to rewrite it just because I can't see it on the smartboard. It was t squared minus 4t plus 3, correct? You probably don't need to rewrite it because it's probably all in one spot. So I take the derivative. What do we know the derivative of position is? Close. That's the second derivative. That's the second derivative. Velocity. When we take derivatives, the derivative of position gives us velocity. So really, when I take the derivative, I'm getting my velocity function.
Ooh, special.
Because when we take a derivative again, we're doing this difference quotient. So you don't have to write down this limit stuff, but just to explain why. F of x plus h minus f of x over h. When we do this, we're dividing basically, just like we did with our secant line. And when we're dividing a distance over a time. These, when we represent them differently, show us the distance over the time. So when you take the derivative, you're basically dividing by time. So when we take the derivative 2t minus 4, we go from being measured in meters to being measured in meters per second. Because by taking the derivative, you can see it with the average velocity a little bit better, but by taking the derivative, we're actually dividing by time. So by taking the derivative again, what do we get when we do the second derivative?
Acceleration.
Acceleration. So what would acceleration be measured in? Meters per second squared. We divide by time again, and if we divide meters per second by seconds, I'll write it because we're going to talk about acceleration on the next one, so I'll write it down under the acceleration one. But if we divide by seconds again, we get meters per second squared. So s prime of 4, we just plug in 4. 2 times 4 minus 4 is 4. meters per second. The instantaneous velocity at 4 is 4 meters per second. That means on our graph again, if I drew my tangent line here at 4, the slope of this tangent line would be 4 over 1. It's a pretty steep tangent line. And it's saying at that particular moment in time, we're going 4 meters per second. So let's see if our applet matches that. No, it's still running. So I'm going to reset. Come on. Maybe I am. Ugh. Stupid Smarty. Go away. Okay. Reset. We're stuck. Come on. Do something for me. I don't know why it will not read. Okay. So now we're at time 0. It already tells us our velocity. We're going to be starting out with a velocity of -4. And we're accelerating at 2 meters per second squared. So we still have negative velocity. We're almost to time equals 1 second. Still have negative velocity. All of a sudden at like 2 seconds or so, we start going positive velocity. We're getting faster and faster. Almost. I could almost stop it at the exact moment. So we are, as we go to the right, getting faster and faster. And it would keep getting faster forever because of our graph. If we look at our graph, what's going to happen if I take the slope at t equals 7? It's going to be even steeper. Eventually it's going to get to the point where it looks like it's infinitely steep. But that's just because we can't draw things like that 100% accurately. So if we're going to find acceleration, we know acceleration is the derivative of velocity or the second derivative of position. So we know if I take the second derivative of position or if I take the derivative of velocity, that's when I get acceleration. And again, we're dividing by time. So we're dividing meters per second by seconds. Which is the same as meters per second times 1 over seconds. Or in other words, meters per second squared. So acceleration again, and we've talked about it a little bit before. Acceleration is how fast your velocity is changing. I could walk from here to here and get faster. I'm starting out kind of slow, getting faster, 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 faster. And I'd have a certain acceleration. We'll say a slow acceleration because I didn't go that fast. But if I went that same distance, and I went there as fast as I could, which is not very fast, but I increased my velocity a lot quicker, that means my acceleration is a lot quicker. I got faster quicker. Does that make sense? So to find acceleration, we just take the derivative again. What's the derivative of velocity? 2. So if I want to find the acceleration at 4, and I could have written S double prime of t to represent acceleration. I could have written B prime of t to represent acceleration. Or I can write A of t to represent acceleration. All 3 of these would be acceptable ways to say, this is acceleration. We have to know that all 3 of those mean acceleration. So A of 4. What would happen if I plug in 4? Still 2. When there's no actual t value to plug stuff in, just 2. If I said plug in negative 5 billion, still 2. Doesn't matter what we plug in. Our acceleration would always be 2 meters per second. That doesn't necessarily mean you can't have acceleration that varies. It just means on this particular problem, the acceleration, you're always getting faster 2 meters per second squared. Your fastness is increasing. Yeah. Velocity and acceleration are kind of weird. So the last thing we would want to talk about is the motion of the particle. When is it moving forward? When is it moving backwards? Where does it start at? Things like that. Where does it end up at? So let's look at our graphs that we have. We have a velocity graph, we have a position graph, we even have an acceleration graph. So position was the parabola t squared minus 4t plus 3, right? So we need to know how to graph this parabola. What would be the best way to graph this parabola? Let's assume we don't have a calculator.
Plug in t values.
Okay, we can plug in t values. How do we know when we found the vertex of our parabola, though, if we just plug in random t values? So what are some key features on a parabola that we know how to find?
How far left or right it is?
Okay. How far left or right it is in relation to the x-axis, is what I'm assuming you're meaning. So like where it crosses the x-axis. How do we find where it crosses the x-axis? Zeros. We're looking for the zeros. So this can give us some key points by setting it equal to 0. Once again, we're assuming no calculator just to make sure we can also do this by hand. So if I factor this out, we want numbers that multiply to be 3, but add to be negative 4. Negative 3 and negative 1, negative 1 and negative 3, doesn't matter which order. So what are our two values that where we cross 0? 1 and 3. So if we know our zeros, we know our vertex value. Where is our vertex located in relation to the zeros? Halfway between, exactly in between. So our vertex would be at 2, but we still do need to know the y value that goes with it. So if I plug in 2 squared minus 4 times 2 plus 3, which I think we found earlier as well, negative 1.
Yeah.
So these 3 points are basically all we need to know to graph a parabola. We might also want the y-intercept. How would I find the y-intercept?
T equals 0.
When t equals 0. So if we plug in 0, we get 3. So here's our position function. We also had a velocity function, 2t minus 4. So velocity is 4. We go up 2 over 1, up 2 over 1. I am going to cheat because I suck at drawing straight lines on a smartboard. So now we have both our position and our velocity functions. And they can tell us some stuff about our particle. Where did our particle start? Our position can tell us where our particle started. So we're looking at the position function. The parabola was our position function. So what is our starting value when time is 0? And that's correct. So when our t value was 0, we had a starting position of 3. So describing the particle motion, we know we start at 3. So we started at 3. After 1 second, so my particle started over here at 3. Again, assuming the smartboard is 0. We'll say that eraser on the smartboard is 0. After 1 second, where did the particle go? What's the position value at 1 second? 0. So the particle moved over here. What about after 2 seconds? I'm going to move out of the way of the board so you can see. -1. So then after 2 seconds, the particle, and notice the big change in speed. I started at 3. I went from 3 to 0 in 1 second, and then from 0 to -1 in another second. That's a big change in speed. It only took me 1 second to move 3 spaces, whereas the second I only moved 1 space. So usually we consider the particle facing forward as in facing the positive direction. So really I should be walking backwards 3 spaces, backwards 1 space. What direction does the particle move at t = 3? Where is my value? Back to 0. So now I'm moving forward just 1 space, and then t = 4. Sorry. 4.
Oh, it's 3.
It is 3 again. That was just, my drawing was not super nice. So it's 3 again. So basically this is the motion of my particle. I start at 3, I quickly, a little bit slower, and then quickly back to 3. So, we know we started at 3. When did my particle stop moving backwards and start moving forwards? What time value did my particle? 2. So at t = 2, so I start at 3, walked backwards, so start at position, so time = 0, s of t = 3. I walked backwards from t = 0 to 2. And then I momentarily stop if I have to change velocity, or if I have to change direction from moving backwards to forwards. Technically I stop, even if it's only for an instant. So I stop at t = 2. Just briefly, barely, pause for even a second. And then I started walking forwards again. From 2, basically forever. In context of a real, real life example, we'd probably have a limit. We'd say we're only considering the first 10 seconds, because obviously we can't measure time forever. So that was by considering the position function. Now let's look at the velocity function. We said I was walking backwards from 0 to 2. So that's my velocity function from 0 to 2. I stopped at t equals 2, so there's my velocity function at 2. And I walked forwards after that. How's my velocity function related to these concepts of walking backwards, stopping, and walking forwards? What's different about the green part of my velocity function compared to the red part?
It's negative in the y direction.
It's negative in the y direction. So this green part, it's below the x-axis. Or negative in y direction. So then what can we say about the red part? It's above the x-axis or positive in the y direction. So if we know our velocity function, it can tell us when we're walking backwards and forwards. In other words, if I'm walking backwards, what kind of velocity do I have? Negative velocity. Backwards implies a negative direction. If I'm walking forwards, positive velocity. So if my velocity function is below the x-axis, I'm walking backwards. If my velocity function is above the x-axis, I'm walking forwards.
So does that mean we can have answers that have negative velocity?
Yes. So that actually brings up a very good point. If we have negative velocity, that implies a direction. But what if I ask you about speed? What's the difference between speed and velocity? So we know if I have velocity, velocity implies direction. That is different from speed. Speed, I don't care if I'm moving forwards or backwards. Speed is just talking about how fast am I going. So if we don't care if I'm moving forwards or backwards, then speed would be the absolute value of velocity. Because speed is not taking into account direction. So we don't care if it's positive or negative. We just want the absolute value. We just want the measurement of speed, not the direction you're moving in.
So if you're taking speed, then it's going to be positive. It just is how fast you're moving, whereas velocity can be negative.
Correct. So the last thing was when we stopped. How do we know on our velocity graph when we stop? Because y equals 0. So we've learned some things from our graphs. We can interpret our position graph. We're a little more used to that from some of our other math classes, but interpreting our velocity graph. Velocity graph. When y equals 0, the particle is stopped. When velocity is negative, or the other way to interpret it, velocity being negative is below the x-axis. Those two things mean velocity is negative, then the particle is moving backwards. And when velocity is positive, or in other words, above the x-axis, those are two different ways to say the same thing. Just like instantaneous rate of change and derivative and slope, there are three different ways to say the same thing. The particle is moving forwards. So when we interpret a position graph, we're literally just finding how far we are away from zero. When we're interpreting a velocity graph, we're more talking about the motion. We're moving forwards, backwards, are we stopped? Whereas when we interpreted the position graph, we said, oh, at time 2, we are literally at -1. So compared to 0, I need to be 1 away from 0 to the left. So let's say instead of starting with position, let's say I start with velocity. Does everyone have this down before I move on this? So we're actually, I think, going to finish with this example, and we'll do free fall next time, tomorrow.
Free fall, do we consider error resistance?
No. We are not that awesome. It's your basic -1/2 times gravity t squared plus v naught t plus s naught. It's your basic. So if you've done physics, you've probably seen it before.
Not that awesome at all. It's really just
I can't
that
remember. It was
learn.
from sophomore year.
So,
not
and we'll write down the
ways
formula and whatnot.
error falls.
Okay, so this time we have a velocity graph. We don't even know anything about position. And I had to add in the tick marks so they're not 100% evenly spaced. Just pretend they are. So we're starting with position, and we just learned how to interpret, we're starting with velocity. We just learned how to interpret a velocity graph. How do we know when a particle is moving forward on a velocity graph?
It's above.
Above the x-axis. So, forward, we want an actual interval. Where would our interval start? Where does our interval start being above the x-axis? At 0. Where does our interval end being above the x-axis? Seven, 8. It's kind of hard since graph is up on the screen, so you can't physically count like I can. So what about backwards? Where would our backwards movement start?
8.
At 8.
Is that where it stopped?
It stopped exactly at 8. Our particle, and like I said, anytime you go from moving forwards to backwards or backwards to forwards, at that instant, even just if it's a tiny, tiny instant, like you can't even really see me stop when I do this, but I stop for just a second. My velocity is 0 for just an infinitesimally small amount of time.
So you use the bracket instead of the parentheses?
IAP people will take it either way. You could but they'll consider it correct either way for this kind of problem. So good question, but not really a huge worry for the AP test. So 8 to 10, 11, 12, 13, let's say it stops at 15. And then when is our particle stopped?
8 and 15.
And
That's
0. And you can write a list with commas, and they still are all t's. I don't have to write t equals 0, comma t equals 8, comma t equals 15. So now we've taken it one step further. They also ask, when is our particle speeding up and slowing down? Zero through 2, what's going on there, Evelyn? Speeding up. It's getting faster. When do we remain at a constant velocity? 2 through 6. And then we start to slow down. So the particle, I always forget I'm the opposite. No, yeah. Doesn't matter where I start, but this is the positive direction for you guys, right?
Yeah.
So I speed up a little bit, and then I do a constant speed for a little bit, and then I slow down until I decide to go backwards. And then what's going to happen from 8 to 10?
It would accelerate.
So you're going backwards, but am I speeding up or slowing down as I go backwards? From 0 to, remember we're talking about speed right now, not about velocity. So I don't care that I'm going backwards. I just care if my speed right here, my speed is 0. What's my speed here? -1 is my velocity. What's my speed?
1.
1. What's my speed here? 2. What's my speed here? 3. So am I speeding up or slowing down from 8 to 10? Speeding up.
Negative direction.
So we're actually, so I'm trying to keep the graph up. That's why I'm writing, instead of below the questions, writing near the graph just so we can see the graph. So we sped up from 0 to 2 and 8 to 10. So we'll be tempted, because it's going down below the x-axis, to say, oh, that means we're slowing down. That's what we want to happen. But velocity-wise, our velocity is increasing. Or our speed is increasing, I should say. Our speed is increasing. The negative part is just saying we're going in another direction, but it's still increasing. Another way to look at it is if you absolute value a graph. Do you guys know how to absolute value a graph? If I want the absolute value, that means all my negatives become positive values, right? So if I just flip the negative part. And then you can see a little easier, hey, speed is increasing. We know we're slowing down from 6 to 8. And from 13 to 15. Sorry, again, it's kind of smushed. You don't need to smush yours like mine. I just wanted us to be able to see the graph while we're interpreting it. And where is it constant? Where is my speed constant? 2 to 6. And 10 to 13-ish. Oh, is it more than that? 10. Yeah. I was considering, yeah, like that. what about acceleration? If we're looking at a velocity graph, now let's consider acceleration of this graph. Acceleration means my velocity is changing. If my velocity is changing, then my acceleration is changing. What if my velocity is not changing? What about my acceleration? It's constant. Well, actually it's zeros. So looking at this graph, we know my acceleration is my velocity is changing from 0 to 2, and it's increasing. So is my acceleration positive or negative there? If my velocity is increasing, what do we know about our acceleration? Positive. Our acceleration is saying we're getting faster. If I have positive acceleration, I'm getting faster. So let's define that again. Positive acceleration. Positive acceleration. Speed is getting faster. Not velocity, speed. So what intervals were we speeding up on? We already found them when we were talking about velocity. What intervals did we say we were speeding up on?
0 to 2 and 8 to 10.
0 to 2 and 8 to 10. So if our speed is getting faster, our acceleration is positive. So how would we know when our acceleration is negative? If our speed is slowing down. So negative acceleration speed is slowing down. Which again, we've already found when we were interpreting just the velocity part. So where were we slowing down on our graph? 6 to 8 and 13 to 15. So another way to consider this graph, I'm going to scroll up to the graph again really quick. So we can flip it to be positive, or you can consider if I'm getting away from the x-axis. So from here to here, I'm moving away from the x-axis. My speed is increasing. If I go from here to here, I'm moving away from the x-axis. My speed is increasing. Whereas if I'm coming towards the x-axis, my speed is decreasing. Whether I'm going up towards the x-axis or down towards the x-axis. So there's another way to think of it as well. Moving away is speed increasing either direction, and moving towards is speed decreasing. So when is our speed constant? So when is our acceleration 0?
2 to 6 and 10 to 13.
Good. So 0 acceleration is speed is constant. So 2 to 6 and 10 to 13. So I know it's weird because we're so used to just interpreting our position functions. We don't often talk about our velocity functions in any of our math classes. In fact, they never even called them position functions before. They just said, hey, here's a function. interpret it. But now we have to be able to interpret our velocity functions as well in terms of position and acceleration, and it is a lot of new things to interpret. So let's ask two last questions about it. When does the particle move at its greatest speed? When does the particle stand still for more than an instant? So when is our speed the greatest? At our constant speeds for this one. It could change if I had something instead of, maybe I had a plinky top, I could say it's just the very top. So our speed is greatest at these constant speeds, because that's when we're furthest away from the x-axis. What about being stopped? Are we ever stopped for more than an instant? What would it look like to be stopped for more than an instant?
You just had it flat on the x-axis.
Yep, a flat line on the x-axis. If I added a little more to my graph, we could say from 15 on, I'm standing still. My velocity is 0 for that amount of time. So we will not have time to start our assignment today. Since we did not make it through free fall, I am going to be changing it a little bit.
While you're at it, you may just want to change it a lot. 3 problems is a really good amount.
Page 136.